So this is the last section in chapter 6, section 6.4. It's called the central limit theorem. And coming from 6.3, and then hopefully you also watch the video on sampling distribution, which has me in it, those things together combine to now talk about the central limit theorem. So what we have in the central limit theorem is we are given some sort of random variable that's from a distribution that is with continuous data, like we looked at in 6.1.6.2. It has a mean of mu and a standard deviation of sigma. Now, what we learned in the sampling distribution video was that the distribution can start out as normal, or it could even be skewed. It can look many, many different ways and still follow the central limit theorem. What we're going to do is we are going to select samples of size n from this normal distribution. What comes from that, what the central limit theorem says is the distribution of sample means. So if you take these samples of size n from a population and find their mean and then put that in a new distribution, the sample means will approach a normal distribution. So we saw that in the last video. So no matter what it comes from, whether that's skewed or really any kind of distribution, that as long as you pick a large enough sample size, your distribution of sample means will be normal. The mean of all sample means is the population mean. So I mentioned this in the last 6.3 video. And the standard deviation of all sample means is what is changed. That's the only thing that's changed. And if you watch the sampling distribution video, which you should because it's like 6 minutes long, it's saying that if you have a parent population like this, the sampling distribution is going to look like this. Still going to be normal, but it's going to look like this. Even if you have a skewed distribution, your sampling distribution is going to look like this. The standard deviation is being changed because you are taking the distribution and as you can see, it's going from here to here. Well, that's standard deviation that's changing. And the way that it changes is taking the standard deviation that you're given from the parent population and just dividing it by the square root of n. That's it. So that's how your standard deviation is changed. So notes about it. As long as you have a normal distribution, your sampling distribution will be normal as well. If the original population is not normally distributed, so if you have some distribution that's skewed, then you really want a sample size greater than 30 to really be sure that the distribution of sample means will look normal. Now, given a normal distribution, so say we have this very normal distribution here, say that the mean is 10, the standard deviation is 3, and we take samples of size 9, it wants us to find the mean of the sample means and the standard deviation of the sample means. And what I want you to see, what's really important to see, is that, coming back over here, the mean of the sample means is the population mean. There's no difference, they're the same number. We saw that in the last video. And all we have to do to find the new standard deviation is just take the old standard deviation and divide it by the square root of our sample size, square root of n. So the mean of our sample means is 10, just like the population mean. And the mean of the standard deviation of the sample means is simply the old standard deviation divided by the square root of n, which is 9. Okay. And that's going to be 3 divided by 3, and that's going to be 1. And this is just going to still look normal. It's just that, trying to make it kind of extreme here, that the standard deviation is going to be changed, and it's going to cause the normal distribution to look more compact, the sampling distribution to look more compact. Now, even if your data is weird, I mean, it's just some weird data, what the central limit theorem says is if you take samples of whatever size, you do want a pretty big sample size, like greater than 30, then if you make the sampling distribution, you're going to get something that is normal. Now it's going to have a smaller standard deviation than whatever it is in your weird data, but it will look normal, the sampling distribution. So don't get scared here. This is still true. The mean of the sample means is the population mean, unbiased estimator. The standard deviation of the sample means is simply our old standard deviation divided by the square root of n. And so what this does is it allows us to answer questions regarding if we were to take, you know, a sample of people, what's the probability that blah, blah, blah. That's what we're going to be seeing next. I think I have at the bottom of the last page there, that before we just switched, it just has the steps. I didn't include them, but you just want to check, do you have a normal distribution or a large enough sample size? You just find your mean of your sampling sample means and the standard deviation for your sample means, and then you just answer the question like we did in 6.1 or 6.2. That's really all you have to do. So let me show you. So here we have the GPAs of all students enrolled at a large university, and we are told that they are normally distributed. We are told that the mean for all students is 3.02, that's the GPA, and a standard deviation of 0.29. We are asked, find the probability that one randomly selected student will have a GPA greater than 3.2. This is going to take you back to sections 6.1, 6.2, because it's asking you a question from there. This is not from 6.4, but I'm doing it to show the difference. So we let X be a randomly selected student, and we're trying to find the probability that that student has a GPA that is greater than 3.2. Now, we've done this, I'll do these in a couple different ways. I'll use normal CDF because we're using that again. I can use z-scores just like we did in earlier sections. I'll do a z-score on this one. So what I want you to see down at the bottom here is if we were to change this into a z-score, the idea is you can look at this a couple different ways. 0, 1, 2, 3, because I'm going to standardize it, -1, -2, -3. My z-score here is taking the data value, subtracting the mean, and dividing by the standard deviation. And that tells me that I want a z-score that is greater than 0.62. And then what I can do is I can look in my table for a z-score of 0.62, so 0.6, and then the 0.02 up here, and I follow it. And when I do that, I would find that that area, so notice we're trying to find, here is 0.62, something like that. And then I've got all this that I got to shape. And we would find in the table that that's going to give us 0.7324, because it's going to give us area to the left. That's what the table does. We've talked about it. So I want the area to the right. So I'm going to do the complement. All right. And that's going to give me 0.2676, and that's about 0.268. Okay. So the other way to do this would have been to use normal CDF, and you could have done that. It's the same answer, and we saw this stuff in 6.2, so you could have done it that way as well. But here is the question from 6.4. Now, instead of just looking at each individual student in a distribution, we are looking, each of the values in this new distribution are the mean of 25 student GPAs. That's what it is. So whereas in this last distribution, we had our mean here and a standard deviation of 2.9. So this would have been like a 3.31. And I don't have, is that right? 3.31 plus 0.29. Uh-oh, if I don't have this right, it's going to get bad. 4, 5, 6, 3.6, like that. I mean, that's what these values would be. We can add and subtract our standard deviation and get values along here as well. You can do it either way. Over here, although the mean is still the same, so remember, we have 20, only our n here is 25. However, our data is normally distributed, so we don't need a large sample size for this to be true. Now, what we just talked about was that the mean of the sample means is the same as the population mean. However, the only thing that needs to change is the standard deviation. The standard deviation of the sample means is the 0.29, but we have to divide that by the square root of our sample size. And when we do that, we get about 0.058. Now, this is all we need. This is all we need. So if I want to put that on here just to show you, I want you to see that we have a smaller standard deviation. It's no longer 0.29. That's what creates the compact normal distribution here. This is about 0.06. So that's what I'm going to use. So this would give me, the next value would be, maybe I can make this a little bit better. Okay, so, okay, so 3.02, if I add 0.06, I'm going to get 3.08. I'm going to get 3.14. So what I want you to see is by making that standard deviation smaller, it really changes how much is shaded, because we have the same question here, but it's asking about the mean GPA of those 25 randomly selected students. So now notice 3.2 is now way over here, like actually way over here. See how small it is? It's like way, way, way over here. And so we are actually adding up very, very little area. And that's because when you take 25 randomly selected student GPAs, since 68% of them sit within one standard deviation of the mean from the parent population, you're going to get a lot of those values even if you randomly select 25. So when you take the mean of those values, they are going to tend towards the population mean. They're going to be closer to the middle than they are those. You're not going to have as many extreme values anymore, and that's what causes the smush. So to answer a question like this, again, it's no different than what we did before. I mean, it's just slightly different. Notice one thing. I'm going to use X bar instead of X because I'm talking about the mean of a set of data. And I still want that to be greater than 3.2, so that's no different. However, I'll change this to a z-score and then I'll use normal on my next one. The z-score for this is going to be the data value minus the mean over the standard deviation of the sample means. So it's the 0.29 divided by the square root of 25. That's the only difference. I want you to see that that is a difference. But that gives us z being greater than 3.10. Now that is a very, very extreme z-score. Remember, anything more than 2 standard deviations from the mean is unusual. This is a little bit more than 3. So notice we're sitting way out in the tail here with this over on the right hand side. But if we go into the table and look for the 3.10 for our z-score, remember this is area to the right, so we have to do 1 minus from the table. We get 0.9990. So that's a very small 0.001 probability. So very small. So notice the difference here once you are looking at a sample of some certain size. That's kind of the enormous and very big difference between 6.1, 6.2, and then 6.4. But that is the difference. A lot of students, have to spend some time with this because it is a big idea, but I want you to see that this is really the only difference we have besides maybe using this notation right here. Other than that, it's the same. Now, find the probability that, let me grab my pen here, 10 randomly selected students will have a mean GPA between 2.9 and 3.10. So this is still the data from above. This is part C. So we still have the mean of our sample means this is not going to ever change. In this situation, we're taking a sample of size 10. So the standard deviation for our sample means is going to be our old standard deviation, back from the beginning, divided by the square root of 10. And that's going to give us about, I have it here, 0.0917. So what I want you to see, notice this one's a little bit, it's not as wide as the parent population, but it's not as small as the last one because the standard deviation is a little bit bigger than the last one, but of course quite a bit smaller than the original parent population. So this is a 3.02 still. I'm going to use 0.09 just to give me an estimate here along the bottom. 2. I'm going to come over here with a 2.93 and a 2.84. There we go. So notice we want the probability that the mean GPA is between. So this looks very similar to other problems, it's just you have that mean GPA. Now we want between 2.9, something like that, and 3.10, maybe right here. And we shade 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 and we shade. And so I'm going to put the 2.9 here, 2.9, I'm going to put 3.1, but this time I'm going to use my normal CDF. So normal CDF, because this is the same as 6.2. The only difference, change in standard deviation. Now what I want you to try on your calculator to see if you can get the same answer is we have our lower value and our upper because we're looking between two values. We have our mean, we have our standard deviation. So here is where the big change is, and that's, you can in your calculator put 0.29 divided by the square root of 10. I'm just saying you can do that in normal CDF. And the reason to do that over anything else is because it will give you the most exact answer. If you want to use this, typically that's going to be okay, but if you round too much, it may not be an exact answer. Now sometimes your modified standard deviation comes out to be nice, but if it doesn't, well, the best thing to do would be to put it the way that I have it right here. But if you put this into your calculator, you don't need the 1 minus, you don't need anything else. Your calculator knows to go and do exactly what part you've shaded. And you're going to see a 0.713 to 3 significant figures because this is still probability. So what you'd find is that there's a really high probability that if you were to choose 10 randomly selected students and take the mean of their GPAs, that it would be between 2.9 and 3.1. Because again, those means are tending towards the population mean. And that's why you're getting the majority of them sitting closer together. The next problem that you see on your page actually continues all throughout the last page of this, so I'll just do that problem in a part 2 for 6.4.